In this lecture, we talk about regular representation. So consider this finite set like this with a G action. So we can define a complex vector, say Cx, with elements like this. So this AI lies in the complex numbers. So instead of writing the bases like this, we can write it as this E sub xi. So now your vector space here looks like this. So this AI is a complex number. So now to this you can associate a regular representation, so which is essentially a map from G to GLCX. G gets mapped to row of G, so this you can think of as a matrix. So basically, or you can think of as something as a linear action. So this row G, essentially what it does is it takes GLCX to GLCX. So what it essentially do is you're taking this element G here, this element G here, and you're taking this element which looks like this exactly, and then the G acts on GXI. So that is pretty much it. So you're taking this G, and notice that this G comes here, which is essentially the basis Xi is getting changed to GXI, and that's precisely we needed this G action. As you can see here, G action on this. So that's how you get the representation. So this is the representation, and so it acts linearly, as you can see. So thus this matrix representation row of G with respect to the spaces EXI, these are called permutation matrices. Now this is important to know what permutation matrices are, and Wikipedia has a beautiful explanation for permutation matrices. So if you do not know what permutation matrices is, you need to stop here, look at the Wikipedia page and understand, which gives a concrete application for this, for our symmetric groups Sn. So very nice, so that everything here is seen concretely, and it is important for what we say next. So notice that this row G ij is equal to 1 precisely when G acts on xj and sends it to xi. So again, we are thinking in terms of permutation matrices. So if you know permutation matrices, you know exactly what we are doing here. So you are just taking the identity matrix and interchanging its rows or columns so that you can send one basis to another basis. So you're taking identity matrix and you are permuting its rows and columns to send one basis or to another basis. So permute rows or columns of the identity matrix. So again, it's important to see what permutation matrices are on the Wikipedia, because it actually shows you this permutation of rows and columns of the identity matrix. So if we are considering only the entries on the diagonal, because we are talking about the characters, and the characters is the sum of the trace of the entries in the diagonal, so we are only considering entries on the diagonal. So the non-zero diagonal entries are precisely which are 1, because there is 0 otherwise. As I said before, it is just permuting the rows of the identity matrix. So the diagonal entry, if it is non-zero, is just 1, because identity matrix just has zeros and ones. So these are precisely those xi which are fixed by this G. So that is gxi on the basis is xi. Now, as I said before, summing the elements along the diagonal gives a trace or the character, which we will denote by pi and call it the permutation character, because essentially underlying everything is the permutation matrix. So if you're thinking in terms of characters, then the character, the Cx, is just this permutation matrix. And as I said before, the non-zero diagonal entries are those which are fixed by G. So you're adding everything up. So this is just the size of this group, which is everything which is fixed by G. So all the elements which are fixed by G, so those will lie on the diagonal. So this is the permutation character. So this is special, that's why we denote it by pi of x. So setting x equals to the group G, so this x can be just group G, because G acts on itself. So you get pi of G is just the order of G if G is E. So because you just have the identity matrix here, because everything is fixed. And notice that it is 0 otherwise, because any other element will permute, because only element which fixes everything is the identity. So any other thing is going to permute, so you get 0 otherwise. So this is important. So notice that we are talking about CG here, not general CX. We are talking about just the group G. So notice this G here. So it is not X, it is just X is G. So now we come to a lemma where we are going to use this. So let there be a finite group G and it has irreducible representations V1, V2, Vk. Then the regular representation of CG will decompose like this. And we have seen this Ni is nothing but the dimension of this vector space, which is just you're adding the entries of the identity on this vector space to get the character. So this is nothing but trace of the identity matrix which acts on this vector space Vi. So therefore when you add it up, it just gives you dimension of Vi. Now the decomposition will follow from the fact that if this chi of CG is like this, then you can actually know the orthogonality of characters, and for every term you should get Ni. So if you take chi of CG with chi of V1 should give you N1. So this is what we will prove. So this decomposition like this follows if this fact holds. Now we have to prove this fact. So if we prove this, we are done, because if this holds, then there is a decomposition like this. So now you take the inner product standard result, this conjugacy of chi G G. So we have seen that if it is identity, you get the order of the entire group, otherwise it is 0. So that is it. So 1 over this is just this and comes here, because this only works for identity, everything else is 0. So this comes for G equals to E. For everything else you have 0. You get like this. This G and G cancel out, and we have seen this before. This is just Ni. This trace of the identity matrix which acts on the vector space Vi is Ni, and therefore we are done. Now you have this decomposition. So chi of CG looks like this. Yeah, so this decomposition looks like this. Now you evaluate it at the identity. So then you get, if you evaluate it at the identity, you get the order of the group on this side, and then here you are evaluating at the identity, but this is just, as I have said before, this is just N1, this is just Nk, this is square, and this is again you have this. So the size of the group is sum of the squares of the dimensions of the irreducible representations. So now we end this lecture with the important remark. So consider the trivial G subspace of Cx. You can think of it as an identity matrix, or you can just think of it as a span of this. Now you can put a G action on it, but it's just going to permute this thing. So this pi x contains the trivial character chi of 1. So now you notice that if you take the inner product of these two terms, this is 0 for this summation as 0. So we know that the G invariant complement would be this. So invariant complement of this would be this for the trivial character. So this is important to see that this trivial character lies within this permutation character. So trivial character is in permutation character. So later on we will show that you take the permutation character and you subtract the trivial character from it. This chi1 trivial character we can denote it as 1. This will also be a reducible representation.